Okay folks, buckle up, because today on the Mysteria Archive we delve into a really weird one, the hollow moon. Yes, hollow. Now, this is one of my favourites, so get ready for a wild ride.
One of the big lunar mysteries that the Apollo astronauts were hoping to at least answer in part was what is inside the moon.
There are moments in history when our understanding of the universe seems to teeter on the edge of new discovery. The moon, ever present in our skies, has inspired myths, driven tides, and guided calendars for countless generations. But beyond its role as a celestial companion, the moon remains a focus of mystery, stirring questions that have both fascinated and perplexed scientists and the public alike. Is the moon truly what we think it is, or does its presence conceal a secret about its interior, one shaped not just by observation, but also by bold speculation and confusion? Tonight, we journey into one of the most persistent lunar mysteries, the so-called hollow moon theory. This question, ignited by seismic experiments during the Apollo missions, has been transformed through decades of investigation, debate, and imaginative interpretation. At the root of it all is a singular event, when NASA's instruments recorded the moon's response to an artificial impact. Did those echoes reveal something unexpected about the moon's structure, or did they simply reflect the unique physics of an airless, waterless world? Let's set out to trace the echoes of lunar vibrations, carefully exploring the science, reports, and misunderstandings that led to widespread fascination. Is there a vast chamber beneath the moon's crust? Or is the true answer deeper and more complex, an insight into how we seek to explain the unknown with both science and imagination? What happens when a world without wind or water endures a powerful jolt? And what does ringing like a bell truly mean in the study of lunar geology? At the intersection of inquiry and myth, we find deeper questions about exploration and about how the unknown continues to inspire wonder even in the age of science. Apollo's seismic enigma, the moon rings. On November 20th, 1969, as Apollo 12 explored the lunar surface, NASA's focus included an ambitious experiment, placing seismic sensors on the moon to record its internal tremors. These passive seismometers listened for vibrations from impacts large and small, collecting data for years. The pivotal event came once the astronauts' mission was complete. NASA deliberately crashed the Apollo 12 lunar module's ascent stage into the moon. The resulting impact sent shockwaves through the crust, which were captured by the seismometers stationed on the surface. What was unexpected was the nature of the lunar vibrations. Instead of a brief, fading thud, the moon's crust responded with a tremor that persisted for almost an hour. NASA scientists described it colloquially as the moon ringing like a bell. Unlike Earth, where water within rocks and soil helps dampen seismic waves, the moon's bone-dry, fragmented crust allowed the vibrations to travel farther and last longer. Why was this surprising? On Earth, shock waves are quickly absorbed and lost within a labyrinth of loose rock, water, and shifting plates. The moon, in stark contrast, lacks these features. Its surface is covered in dry regolith, underlain by dense, fractured rock, both the result of billions of years of meteorite impacts and volcanic activity. With no atmosphere, no liquid water, and no geologically active plates, the conditions allow seismic waves to maintain their energy and travel efficiently through the stone. This phenomenon quickly captured public imagination, and indeed, confusion. While NASA's scientists began analyzing the implications for the moon's structure, speculation outside the scientific community skyrocketed. Reports of the ringing were soon taken out of technical context. Some suggested the moon must be hollow or even artificial, theories that would persist and evolve long past the Apollo era. But what really happened? How were the seismic signals interpreted in the first place? And why did they generate so much speculation? To follow the unfolding story behind Apollo's seismic discoveries and what they reveal about the moon's true nature, subscribe now and stay connected as we explore the science, the myths, and the future missions set to uncover even more lunar secrets. Now let's move on. The Apollo seismometers, set up at various landing sites, remained operational for years, recording thousands of lunar seismic events, some triggered by impacts, others by internal stress. Most of the events were much weaker and more prolonged than typical earthquakes, reflecting the unique properties of lunar crust. The crucial detail: the moon's ringing doesn't mean it's hollow like a bell. Rather, it reveals that its rocks are extremely good at conducting vibrations. On Earth, a seismic wave slows and fades as it encounters layers of water and shifting soil. On the Moon, such damping is minimal. The impact energy endures, bouncing off layers within the crust, and even reverberating along existing tunnels or gaps left by ancient geological processes. In scientific terms, the Moon responded to impacts with long-lasting vibrations because of the way its dry, compacted crust transmits waves, an effect sometimes compared to a tuning fork. Rather than suggesting vast empty spaces, the phenomenon points to the rigidity and dryness of lunar material. The Apollo seismic data confirmed that the Moon is mostly solid, but is not without features formed by volcanic and impact processes. Moonquakes, monthly events detected by Apollo's instruments, were typically weaker than earthquakes, but lasted much longer, again due to the efficient transmission of energy. These moonquakes were triggered not by plate tectonics, which the Moon lacks, but by tidal forces from the Earth. Temperature extremes at sunrise and sunset, and occasional meteor strikes. What about the idea that NASA confessed the Moon was hollow? In reality, NASA and associated scientists clarified that the ringing was a product of geophysical properties, not evidence for hollowness. Rigorous studies have since shown that the Moon has a crust, mantle, and core broadly similar to Earth's basic structure, though with important differences in composition and size. The rise of the hollow moon theory. The hollow moon idea predates the space age, but gained new energy following Apollo's seismic results. Science fiction writers and speculative thinkers latched on to the notion that the Moon might contain vast cavities. In 1970, two Soviet researchers, Michael Vassin and Alexander Shcherbakov, went so far as to propose that the Moon could be an artificial spaceship, a theory entirely unsupported by geology but powerful in its imaginative appeal. Such ideas soon entered popular culture. Enthusiasts pointed to the unusual longevity of lunar vibrations, odd surface features, or patterns in craters as evidence of artificial origins or massive internal voids. However, no scientific study has ever found evidence of large cavities within the Moon's interior. Direct seismic measurements, gravity mapping, and lunar sample analysis all point to a naturally formed, mostly solid body marked by complex geology. Nonetheless, smaller natural voids beneath the surface do exist. These features, formed by the Moon's own volcanic processes, would have important implications for both geology and potential future exploration. Lunar lava tubes, natural cavities. Modern missions, such as NASA's Lunar Reconnaissance Orbiter, LRO, have provided dramatic new views of the Moon's surface. High-resolution imagery revealed features known as skylights, collapsed ceilings of ancient lava tubes. These are not evidence for a hollow moon per se, but instead point to vast natural caves carved out by lava flows billions of years ago. When the Moon was geologically active, flows of molten basalt moved beneath the surface, creating tunnel-like voids. As the lava drained away, it left behind large tubes. Most have collapsed, but some appearances, such as round pits, deep crevices, and unusual subsurface signatures, are visible from orbit. Some lunar lava tubes are believed to be much larger than those on Earth, owing to the Moon's weaker gravity. These features have fascinated planetary scientists and become targets for future exploration. Lava tubes could provide natural shelter for astronauts, protecting against radiation and micrometeorite impacts while being stable enough for potential bases. What does this mean for understanding the lunar ringing? The presence of natural tunnels and cavities beneath the surface would slightly change how seismic waves propagate, producing complex echoes in local areas. However, these are not empty caverns on the scale required by hollow moon theories, but rather geological features observed in other volcanic worlds. The real science, what Apollo discovered. Through decades of measurements, scientists constructed a model of the Moon with three broad layers: a crust, a mantle, and a small, dense core. Seismic waves from lunar impacts and moonquakes behaved as expected for a rocky sphere, with the unique twist that the Moon's dry materials let signals linger far longer than on damp Earth. The bell-like ringing refers to the persistence of vibrations, not to a literal metallic shell or resonance found in a hollow structure. NASA's technical papers, far from confessing a remarkable secret, instead presented a detailed picture of a dry, mineral-rich world with its own record of ancient volcanism, crustal fractures, and cooling processes. NASA's statements and peer-reviewed research all confirm the Moon is not hollow. It is, however, a place of scientific fascination, with hidden tunnels, complex layers, and a rich geological past. Recent research, much of it based on orbiter and gravity data, has revealed continuing changes within the Moon. As the Moon's small metallic core cools, the outer layers contract, forming thrust faults at the surface, visible as cliffs and ridges stretching for kilometers. These contractions trigger modern moonquakes, showing the Moon remains geologically active in subtle ways. The processes responsible for the Moon's structure are familiar to planetary scientists: cooling, volcanic activity, and heavy bombardment by asteroids. Some of the heavy metals measured within the crust, such as iron and titanium, formed as the Moon differentiated after its birth from a massive planetary collision. These dense rocks subtly affect seismic wave transmission, sometimes amplifying or scattering vibrations within specific areas. There are no indications of artificial or unnatural internal hollows. Instead, what Apollo missions and later studies uncovered was a radially layered structure with some subsurface tunnels, a far more plausible and evidence-supported explanation for the Moon's unusual seismic properties. The persistence of mystery, science, and imagination. Why has the idea of a hollow or artificial moon persisted for so long? At least part of the answer lies in how humans respond to the unknown. Scientific discoveries often arrive with results that seem counterintuitive or difficult to interpret without deep context. The moon's prolonged seismic echoes were new and startling, unlike anything previously measured. In popular accounts, this easily translated into wild stories that overshadowed the slow, cumulative process of scientific understanding. With every decade, new missions deepened scientific knowledge and corrected previous misconceptions. The more scientists mapped the moon's gravity, composition, and seismic behavior, the clearer its true nature became. But for many, the poetic image of a ringing moon retained its allure, a symbol of unanswered questions at the border between fact and fantasy. Today, the scientific consensus is clear. The moon's strange seismic responses are fully explained by its geology. The presence of natural tunnels and metallic-rich layers enriches our understanding, but does not point to vast, empty hollows. In fact, the real mystery of the moon is how much it shares with other rocky worlds and how its particular history as a volcanic, battered, and cooling body gives it its unique signature. Humanity's exploration of the moon did not end with Apollo. NASA, international agencies, and private companies continue to plan robotic landers and soon new crewed missions. The Artemis program, aiming to return humans to the surface for extended stays, is poised to use far more sensitive seismic instruments than were available in the Apollo era. These new missions will map the moon's interior with unprecedented precision. The goal is not just to confirm what has already been learned, but to uncover further details: the extent of lava tubes, the distribution of metals, and the presence of any smaller voids or fractures within the crust. Every impact, whether from a falling meteorite or a rocket stage, adds new data to this evolving picture. Lava tubes, in particular, are a focus because they may become crucial assets for long-term lunar exploration. Their sturdy walls and buried location offer a natural shield against harmful cosmic rays and surface hazards. Scientists and engineers are already preparing instruments to probe these features, mapping skylights with LIDAR and radar, and planning the first robotic missions into their shadowy openings. Meanwhile, discoveries about subsurface metals have piqued interest in lunar resources. Rich deposits of iron and titanium may support construction or manufacturing on future lunar bases, while helping us understand the violent processes that shaped the moon's crust billions of years ago. These initiatives are driven not by suspicion or secrecy, but by scientific pursuit and the promise of new discoveries. Resolution: the real lunar story. So, what is the true legacy of the hollow moon question? The answer is both straightforward and inspiring. The moon is not hollow or artificial. It is a dynamic, layered world whose unusual seismic characteristics spring from its dry rocks and complex history. Rather than vast empty spaces or hidden machinery, what lies beneath the surface is a record of ancient lava flows, impact scars, and the slow cooling of a once molten core. Yet the idea of hollowness endures as a metaphor for how much remains to be discovered. Each moonquake, each reverberating impact, reminds us that even worlds we think we know can surprise us. The echoing signals recorded by Apollo and later missions are not signs of emptiness, but testimony to a natural world shaped by forces both violent and gradual. Science thrives on questions, especially those that persist, challenging us to look closer. The coming era of lunar exploration promises to reveal further wonders, perhaps new skylights that lead into lost caves, new evidence for metal veins running through the deep crust, or the first human footsteps within ancient tunnels. As we listen to the moon's echoes, whether through sensitive seismometers or the stories retold across generations, we realize our satellite still speaks. Its voice is one of geology, history, and cosmic connection. Thank you for joining this exploration of lunar mysteries. The quest to understand the moon continues, not with sensational secrets, but with careful listening and relentless curiosity. As future missions set down on its surface again, humanity will write new chapters in our lunar story. Follow every echo, and you'll discover not an empty world, but a world of infinite complexity and enduring promise.